So this is a hot air balloon. I remember being fascinated by these things as a kid because I had an experience with regular balloons filled with air. They don't float. And regular balloons filled with helium, and they float. But this balloon has big holes in it. There's a hole at the top, maybe not very large, but there's a huge hole at the bottom. How can this thing float? It just didn't make any sense to me. This is a hot air balloon. The reason it floats is because it's full of hot air. You can control it going up and down by changing the temperature of the air, because changing the temperature of the air changes the density of the air. Heating a gas causes it to expand. The mass of the gas doesn't change, but its volume does, so its density changes. Density is the mass divided by the volume. If we make the volume larger and the mass is the same, the density is less. Less dense gases float in more dense gases. Something that's less dense will float on something that's more dense. So if you make the air in the balloon less dense than the air outside, the balloon will rise. That's why helium balloons float, because helium is less dense than air. So Charles' law tells us that the volume and the temperature are directly related. Not inversely, but directly. The volume increases with the temperature. So here's a graph showing the volume of a gas in liters and the temperature in Celsius. So if we start, around 0, and then we increase the temperature, the volume increases, and it increases in a linear fashion. If we extrapolate this line, meaning we draw a straight line through these points and we keep going past where we have data, we find that it would intercept the y-axis 0 at minus 273 degrees Celsius. So there's a 0 at minus 273. So that seems to imply that if you took a gas and you got it colder, it would shrink. And you got it colder and it would shrink, and that maybe you could just keep doing that until you got to minus 273, and then what would the volume be? Be 0. Could that actually happen? What's a gas made out of? Particles and a whole bunch of empty space, right? So you can shrink it down some by making it colder, but eventually it's going to condense into a liquid, and then getting it colder and colder isn't going to cause it to get any less in volume, because the particles actually do have volume. So this is one of those cases where kinetic molecular theory is going to deviate a little from real life. But we look at this and we see there's a 0 intercept at minus 273. When you have the equation for a line, y equals mx plus b. Let's write that down. Y, the vertical axis, is equal to the slope of the line times the value on the x-axis plus b, which is the y-intercept. If this is 0, the equation for the line gets much simpler. And then y equals a constant times x. So we would like this graph to have a 0 intercept. And so the way we achieve that is by changing the temperature scale. This is where the Kelvin scale came from. This idea, this concept of absolute 0, minus 273 Celsius being the coldest possible temperature. It's actually 273.15, but we'll leave that alone. So J.A.C. Charles, he was actually a French mathematician and a physicist, and he studied this relationship between the volume of a gas and its temperature. And this is back in the 1800s. So his law assumes that we keep the pressure constant, because we know that changing the pressure will change the volume. So we don't want to mess around with that. We'll leave the pressure constant, and the amount of gas constant, and we're just going to look at the relationship between temperature and volume. So his law says that the volume of a gas and its Kelvin temperature are directly proportional. And the way this is usually written is V1 over T1 equals V2 over T2. This doesn't work if you use Celsius or Fahrenheit, because then that graph has a non-zero intercept and the line is not y equals mx. So when the temperature of a gas sample in kelvins is doubled, its volume doubles. If you look at the temperature in Celsius and double it, the same thing does not happen because of the relationship between Celsius and Kelvin. It's just an offset. Okay? So whether you understand that or not, temperatures must be expressed in kelvins. That's probably the most common mistake students make, is they forget to convert to kelvins. In all these gas problems, we have to use kelvins. There's just no way around it. Kinetic molecular theory explains this. If the temperature of a gas sample is increased, the particles move faster. If we want the pressure to stay the same, we have to increase the volume. If you just increase the temperature and don't allow the volume to change, then the pressure is going to change. This is something you can try at home. Blow up a balloon, just kind of medium full. Stick it in ice water. It'll shrink. Take it out, put it in boiling water, watch it get bigger, and go back and forth, back and forth. The volume of a gas depends on its temperature. So of course we can do calculations. We've got 2 minutes, we can do this. A sample of gas has a volume of 2.8 liters. We're going to do this whole table thing again. 2.80 liters as a volume of that at an unknown temperature. When we submerge it in ice water at 0 degrees Celsius, okay, so 0 degrees Celsius, its volume decreases to 2.57 liters. What was the initial temperature? Well, here's our table. This first column is what? Volume, and the second one is temperature. So here's our blank, T2. What's wrong with this temperature, though? It has to be in Kelvin. So our equation is V1 over T1 equals V2 over T2. Cross multiply and get rid of those fractions. V1 T2 is equal to V2